sell, I think it's something like $5 for 2 or 3. I couldn't afford not to do it, so I went ahead and bought 144 for $144. So that I always have enough, because these are cool. Originally I used to be able to pay the Oriental Trading Company $3 a dozen. Okay? And it's kind of Ron's getting in. I'm getting around really bad time.
Pretty good to see. Just decided to leave.
So Bernoulli's law says that faster moving air draws air in from the side, or air from the side pushes in because of the lower pressure, right? Faster moving air creates a lower pressure on either side. So all I have to do is, this is what gets the kids to go, whoa! There's one breath. There's 2 breaths. And then we can tie that into a knot, and then we get to play with air. And this is one, and if you need to give them a reward, just go off game, let them play with air. Most people
This chili cheese.
Oh no, that's nice. That's where I'm digging it. That's where I do Parks Burn. That's one of the ones on the video. But then you take this and you can shoot these around the room. And you can see that there obviously has mass, displacement things, it's volume. No matter how hard it hits, I know that educational innovation has I got the roll of 144 from them, but they still have over there on the stuff just over there trying to get some other things, and they had like 3 pack or 2 pack, whatever it is, and so it's a Carbon is number 6, its weight is 12. Nitrogen is number 7, its weight is. Carbon's number 6, its weight is 12. Nitrogen is number 7, its weight is. Oxygen is number 8, its weight is. So 2 oxygens together, like we breathe, weighs 16 plus 16, or carbon dioxide has the 2 oxygens for the 32 plus the carbon, which weighs. So the total is 44. Which is heavier, oxygen or carbon dioxide? Okay. So now I have a bunch of carbon dioxide in there. Next, I'm going to get bubbles.
Bubbles?
Bubbles. Bubbles. Bubbles.
Yeah, bubbles. I'll put in this one too. If it blows up, I'll make it bubbles. Whoa, cool. Oh. Do it again. Hey, dude, watch. Watch.
Oh, missed.
Watch the bubbles bounce off. Look the bubbles.
It is floating. It's floating on top of the carbon dioxide. It's kind of hard to hold this and. Okay, you blow the bubbles. Pretty bubble. I missed a lot too. They're crummy, cheap bubbles. There we go. There we go. There we go. We got a floater. There we go. See it floating? There we go. We got a floater. See that one floating there? Oh, that's a nice float. That one's a nice float. Don't pop it. We got a good solid float. Look at it floating there on top of the carbon dioxide.
Some more. Aw.
There we go. There's several of them floating in there. There we go.
Matt, look at the bubble in there. It's like, it's going down in there.
Carbon dioxide, you recording? Yes. Okay. Carbon dioxide weighs 44, oxygen weighs 32. Butane, because it's C4, that's 48 for the carbon, 10 for the hydrogen. Oh, there we go. We got a leak through here. Okay. Let's try that again. All right. Here we go. I'm going to fill this with butane. This is getting haphazard. Okay. Fill this with butane. Butane's heavier than the other gases in the room. Therefore, all the others were pushed out. The only availability for our fire is with the oxygen on the outside. The rest is all filled with butane. If I close off the availability of oxygen, it no longer can burn. There is still butane in there. It's down at the bottom. As you can see, all I have to do is open it up. But there's still some butane in there. And I can demonstrate the butane is in there by pouring it into this beaker. You may or may not be able to see it pouring into the beaker, but it pushes all the other gases out so that the beaker is now filled with butane, so that if I light it at the top, it burns slowly down to the bottom. Okay, thank you. In on that one. This is something that I think is worthy buying. This is something you end up having to pay money for. It's the expensive one. You get this little screw-in device, and it's got a piece of plastic. Now, the person that I saw this demonstrated at a conference once, and the person that demonstrated it at the conference said, you know what, I don't care whether you buy it from Steven Spangler or not. You can get it from Steven Spangler if you can't get it anywhere else. But all you have to do really is put some sort of hook on some sort of plastic sealable rubber. You use inner tube rubber or some other such rubber. And you place it on an object, you place it on a stool, and I want to make sure I don't pull the glass out. You know, that would be devastating. But you see, it's about the air pressure on top that's holding it down. This is, what is it, 1,000 pounds per square foot. This is a square foot. So there's 1,000 pounds of pressure on top of this against this, and this is only a few pounds. But if I slide sideways now, then all bets are off. But you know, so that it's not really suction, it's about pressure. Pressure is always greater pressure to lesser pressure. So there's no, you know, unless, now we've talked about what are the elements of the universe. There was the bosons and the gluons and the, oh yeah, we've got a fifth element of the universe, pullons. They explain suction. And they explain my pulling on your leg. I'm sorry, pullons. Anyhow. You'll notice on this clip that I have a light source that is a flashlight with a tube around it. I've got it shining a circle on the piece of paper that is perpendicular to the light. You'll notice that as I'm shining it at a perpendicular to the light, I draw a ring around it, and that becomes 1 unit of light that impacts upon the perpendicular. Now this is what you'd get at the equator. This is what you'd get during very close to summertime. Now if I tilted it at about a 30-degree tilt, you'll notice that the area that same concentration of light hits on is almost twice the area. That's at about a 30-degree. This would be what we experience at wintertime. This is why it's colder in winter and warmer in summer. We get about half as much radiant heat per unit area. At the perpendicular, we have the full concentration of the light. At the 30-degree angle, you're getting approximately half the amount of light,
or energy, and this is why we have winter when the Earth is at such a tilt.
Going 22 miles an hour. Pretty cool, huh?
Candles, everybody's seen them burn. A candle might be convenient in space were it not for the lack of gravity in space, inside a space capsule. Candles require gravity because the light heated air has to rise, and the cooler air from the outside containing oxygen has to come back into the wick. I will often ask a question of my students, and you can ask questions of your students. When you've got a candle burning, what's burning? And of course, the candle's a wonderful thing. It's solid, liquid, and gas all in one item. You have the solid of the wax that's holding the candle. You have the liquid that pools up around the wick. And of course, the vapors coming up. Most of them would say the wax. Most of them might, or some of them might say the wick. But if you light the candle and you get a good flame going with the candle, you get a side stick like maybe this bamboo skewer here, and you light it on fire. There's a source heat. You can often blow the fire out, holding the fire in your left hand with the stick, the burning stick, blow the fire on the candle out. See the vapors rise. And if you look very carefully, you'll be able to see that it is the vapors rising off the wick that reignite. So this is done because of convection current. Convection current makes this possible. Okay, blow it out, and you see, if you look carefully, you can see the vapors ignite. Blow it out, vapors ignite. Blow it out, vapors ignite. There we go. That one was a good show. Alrighty. And here it is in close-up. This way you ought to be able to see it much better. There's the stick burning. There's your source stick. You blow out the fire. A little puff of air is usually best. There you go. You saw the vapors. That way, up close, you're able to see that the vapors were actually what was burning. Blow it out, and the vapors are what ignite. Blow it out, and the vapors ignite. There we go. This is a Ditto Master. You'll notice that this is something older teachers used to use a lot. This Ditto Master may be laying around some of your schools. The front part here is the part that would do the transferring of the print. And down in here, this would be the Ditto Master Protector. It's used to protect the integrity of the ditto. A teacher would perhaps make a drawing on the outside or do some writing, depending upon the grade level, and something they wanted to pass out to the class and make copies of. Then they would take and tear off the front cover with the ink transferred from right below the front cover, put it through an alcohol transference thing, and it'd make 50 to 100 copies. See, this is my happy man jumping up and down. And you'd peel that off when you got over to the work lab. You'd pull the front part off, and it would do the transferring of the ink. And then the Ditto Master Protector, and it would all go into the trash. Once they were in the trash, they'd get hauled off to the dump, crumpled up, and so forth. Somebody would usually start a fire in the dump. And so, it's crumpled up, it's gone to the trash, and there's the Ditto Master Protector. Gave its life to protect the integrity of the Ditto for all mankind, students alike. It gets the fire starts in the dump, and there's the Ditto Master Protector burning away, unappreciated, unwanted. God looks down on this and he says, "Oh, this is more than I can take. I'll take the Ditto Master Protector." This demonstration was accomplished using a series of these plastic containers stacked in opposite directions so that there was a little bit of a gap between them. And by being able to draw, so there's a little bit of a gap, and then be able to draw sequentially with a dry erase pen or some sort of felt pen on each of them in series so that you could get a three-dimensional effect. This way you can do them in sequence. So you can draw a line here, a little darker. And then draw a second line here. And you can see three-dimensionally.
With a cold front, the slope is much steeper and the warmer air ascends up over the front of the cold front. You'll notice the air ascends up over the front and backwards from the direction of movement of the cold front. The cold front moves into a warm area, and the heated air rises and goes behind the actual line of the front. With a warm front, the hot air goes up over the cold layer, and so the front itself actually ascends over the top of the cooler lower layer. The slope is going to be a very steep slope.
You will notice that as the cold moisture goes down in the middle, it will descend through the middle column and will go clockwise outward from that center column. This is what you have in a high pressure system. High pressure system descending in the middle and going out clockwise from the center. Low pressure, column up, counterclockwise.
All right, now you guys don't get in the way of my recording, please. All right, now, you'll notice the fire's not particularly high. The fire's not particularly high, but as soon as I start to spin it, I start to increase the, it say I'm spinning it counterclockwise. And you'll see that as I spin it, the fire, if I stop spinning it, the fire gets smaller. As I spin it, there's more oxygen availability. There's a lower pressure in the middle. It's rising in the middle. There we go. And you'll see the fire is much higher when we do it that way. Ah, there we go. That's what we're talking about. And now you get to see what a low pressure zone looks like.
What's this stuff?
Sir, what does this do?
Dry ice.
Why is it dry?
It's gonna sublimate.
Sir, can I hold a piece?
No.
Sure, I want you to hold it on your tongue. Maybe swallow a tab or two. All right, you're ready. You're ready to hand me the cap.
A little bit.
Okay.
Recording? Ready? Start now?
You recording?
Yeah.
Okay, we're adding hot water to this.
Oh my God, we're close to it.
Yeah. Give me the lid. Okay. No, we don't need to record this part. We'll need to record the bomb.
Oh!
All right, here we go. You see it? Yep. Okay. Solid, liquid, gas. Okay, you can stop. Okay, this is going to be called cold boil. I'm going to use this propane torch, this round bottom flask, and I always got to recommend that this be done with a round bottom flask because normal flasks, even Pyrex flasks, may not have the strength in order to be able to handle the the pressure that will be applied to the outside of this flask. So round bottom or sphere is the only thing strong enough to be able to handle that. Time passes. Now, often this is a point at which I ask my class and make sure they've memorized. The boiling point of water is 212 degrees Fahrenheit or 100 degrees centigrade. So my thermometer at present is a centigrade thermometer. So when I put the thermometer in, I would expect that it will read about 100 degrees centigrade. 100 degrees centigrade? Okay, so we're boiling. You put the fire out. Okay, so we got boiling. And it says it's, you can still see that it's indeed boiling. So we're boiling right here. The temperature it reads right now is, well, it says it's boiling and it's still only at 94 degrees. So yeah, I've got it down to 82 degrees. Yeah, 82 degrees. Oh yeah, we're down to 76 degrees. Okay, 76 degrees centigrade. Okay. That has to do with, you see, I lower the pressure by making the vapor try to condense. As we lower because it's still boiling. And now, let's hold my hand. There's boiling water in my hand. Boiling water coming in my hand. Still boiling at 53 degrees. Still boiling after 53. You can see I'm obviously able to hold this in my hand just as it is. Okay, let's stop boiling. I'm going to cool it down some more. I'm still getting boiling up there at the top. See that? Still getting boiling at the top. Still getting it boiling. Get a few buckets. Okay, we're pretty much done at 44 degrees.
Water evaporation.
Show his face, show his face.
Basically, what it does is it stores, creates and stores static electric charges. The way it basically does that is with a belt that turns, and there are brushes that absorb or pull off, peel off electrons from the belt as it goes past the brushes. There are brushes here and there are brushes there. So one is depositing electrons, the other one was retrieving electrons, so that you constantly are generating electrons. And when clouds slide across clouds, they are peeling electrons off or depositing electrons off as they peel past another cloud barrier. So this is the way we get static electricity, which is the way we get lightning. And so lightning tends to be very high voltage, very low amperage. It's the amperage that truly mostly kills. It takes 15,000 volts to jump. Since voltage is more like speed. It takes 15,000 volts to jump 1 inch of air. Oh, I can feel that in my teeth. 1 inch of air is 15,000 volts, so this is generating 15,000 volts to make it 1 inch. Oh yeah. That's at least 2 inches, so that's at least 30,000 volts. That's generating 30,000 volts. And so figure how much it's got to be to jump all the way down to the ground. So it's an incredibly high voltage, and a very low amperage.